Welcome to this session on mastering VariSense advanced features. In this lesson, we're going to dive deeper into some of the powerful tools VariSense offers beyond the basics. Whether you're building a decentralized application, integrating external APIs, or designing secure multi-party logic, these advanced features give you the flexibility and control you need. We'll walk through real-world use cases and hands-on examples, so by the end of this session, you'll have a clear understanding of how to apply these capabilities in your own projects. Let's get started. In this session, we covered 4 key advanced features of the VariSense platform. First, we looked at KV storage. This is a built-in key-value system inside each Nucleus, allowing us to persist small pieces of data like device status, counters, or configuration parameters. We learned how to store, retrieve, and delete data using structured keys. Next, we explored the timer system. VariSense allows you to schedule tasks using the timer API, either one-time or periodic. You can set delays, define timeouts, and register callback functions that are automatically triggered when the timer expires. This is useful for background tasks like polling sensors or retrying network requests. The third chapter introduced HTTP requests. We saw how a Nucleus can make outbound GET or POST calls, set custom headers, send request bodies, and handle responses asynchronously through callback functions. This is ideal for integrating your logic with external services, such as calling OpenAI, triggering webhooks, or communicating with your backend. Finally, we discussed Threshold Signature Scheme, or TSS. Unlike traditional signature schemes where a private key is held by a single party, TSS splits the key among multiple participants. No single party can sign alone, but a subset can jointly generate a signature. Alright, in this section, we're going to focus on key-value storage. I'll walk you through a simple example to demonstrate the main operation step by step. For full API details, you can always check the official documentation. The link is on the screen. Let's get started. In the previous course, we've already seen how to store and retrieve a user. Here, the user structure contains 2 fields, an ID, which is a 64-bit and signed integer, and a name, which is a string. So each user record is identified by a unique numeric ID and stores an associated name. To store a user, we first build the storage key by combining the prefix user with a user ID. The user ID is encoded into big-endian bytes, so keys are properly ordered in storage. Once we have the key, we store the encoded user object using put and later retrieve it using get. This is the basic usage: store data under keys and read them back when needed. Now, let's take a look at deleting a user. In delete_user, we build the key in exactly the same way. Once we have the key, we call del to remove that key-value pair from storage. As long as we know the key, deletion is direct and immediate. There's no need to search. We simply delete using the key. Next, let's talk about fetching multiple entries at once. The function get_users_range allows us to retrieve multiple users starting from a given ID. We build the starting key and call get_range. We specify that we want to scan forward, meaning we start from this key and read keys in order. We also provide a limit to control how many entries we want to retrieve. Now, one important point to clarify. Get_range only returns keys that actually exist. If certain IDs within the range have no data stored, they simply won't appear in the result. For example, if we request IDs from 1 to 5, but only ID 2 and ID 4 exist, we will get back just those 2 entries, 2 and 4. It doesn't return placeholders or empty slots for missing IDs. The values we get back are still raw binary data. We decode each one into a user object, collect them into a list, and return them. This kind of range query is very useful for pagination, batch processing, or listing data efficiently. Now, let's move on to prefix search. In search_user, sometimes we don't have the full key, but we want to find any key that starts with a certain prefix. We build this prefix using user and the ID bytes, then call search. The search function scans forward from this prefix and returns the first matching entry, if any. If we find a result, we decode it into a user object. If there's no match, we return none. Prefix search is especially useful when keys are organized hierarchically. For example, if users were grouped into categories, we could easily scan all users under a specific group prefix. Finally, let's talk about deleting a range of keys. The delete_users_range function allows us to delete multiple entries at once. We build both the starting key and the ending key. Then we call delete_range. This deletes all keys starting from the start key up to, but not including the end key. This is much more efficient than deleting keys one by one, especially when clearing a large batch of data. Alright, in this part, we're going to look at how the timer system works. Timers allow us to schedule functions that will run after a certain delay. The key parts we'll use are init, timer, and the set timer macro. Let's start. First, let's look at init. When we mark a function with init, it means this function will automatically run when the WESM module is deployed or upgraded. We don't need to call it manually, the system handles it for us. In our example, we have a function called timerInit. Inside it, we call setTimer to schedule a timer that fires after 5 seconds. This timer will call testDelay, and we pass 2 arguments, the string nothing and the integer 0. After setTimer is called, this task is registered into the timer scheduler. The contract doesn't block or wait. Execution continues normally. The timer sits quietly in the background. Once the 5 seconds have passed, the system automatically triggers test_delay with the arguments we provided. So every time this contract is deployed or upgraded, timerInit runs, schedules this delayed task, and the timer system handles the timing. Now, let's look at setting timers during normal runtime. In test_setTimer, we first write a simple marker into storage. Then we call setTimer with a delay of 4 seconds and schedule testDelay with 2 arguments, ABC and 123. Again, once setTimer is called, the task is registered immediately. After 4 seconds, the timer fires and testDelay runs with the provided arguments. For testDelay to be called by the timer system, we mark it with timer. This tells the system that this function can be triggered by timers. Inside testDelay, we write into storage to record that the timer fired, and we store the arguments we received. The nice thing here is that we can directly pass parameters when scheduling timers. The system automatically handles serialization and decoding. Now, let's look at scheduling multiple timers at once. We have a function called testSetOrderModTimer. In this function, we loop through 10 values, counting down from 10 seconds to 1 second. For each value, we schedule a timer with the corresponding delay. Each timer will call testDelay with arguments ABC and the current loop value. After this loop runs, we will have 10 independent timers scheduled, each firing at a different time with its own parameters. Timers are fully independent. You can schedule as many as you want, with different delays and arguments. Now, let's move on to a more advanced recursive timer example. Here we've separated the entry point and the recursive function into 2 parts. First, we have testSetPerfectTreeModTimer. This function simply starts the whole process by scheduling the first timer after 1 second. When that timer fires, it will call setPerfectTreeModTimer with I equal to 1 and using time equal to 0. Now, let's look at setPerfectTreeModTimer, which is the actual timer handler. We mark it with timer, so it can be called by timers. When this function runs, it first writes into storage to record which node is being processed, along with the current using time. If I reaches 8 or higher, we stop recursion. Otherwise, we schedule 2 more timers. One for the left child, I times 2, delayed by 1 second. One for the right child, I times 2 plus 1, delayed by 2 seconds. So every time this function runs, it creates 2 more timers for the next level. This builds a binary tree structure where each node schedules its children. The entire process is fully asynchronous. The contract never blocks. It simply schedules the next timers, and the timer system handles all the execution in the background. This recursive pattern allows us to build complex multi-step workflows using timers alone. Now, after we've deployed this Nucleus, let's go back to the Nucleus dashboard and open the timer module. It's already been more than 5 seconds, so let's check the delay variable. We should see that it has been updated by the timer we scheduled during init, and the value should now show nothing and 0. Next, let's test a regular timer. We'll trigger the function to set a new timer that fires after 4 seconds. After 4 seconds, the delay value should be updated to init. And finally, let's test scheduling multiple timers at once. We'll schedule 10 timers, with delays from 10 seconds down to 1 second. Each one will update the delay value as it fires. Alright, in this part, we're going to look at how HTTP requests work inside VeriSense. Sometimes we need to call external APIs, for example, to get data or to interact with AI models. Here, we'll use OpenAI's API as an example. Let's walk through the code step by step. First, we have the function requestOpenAI. This function takes some input text, which we call context. We want to send this context as a prompt to OpenAI's chat completion API. Before sending the request, we need to build the HTTP headers. We prepare 2 headers: the authorization header with our OpenAI API key, and the content type header, which we set to application/JSON. Next, we construct the HTTP request. We set the method to post, the URL to OpenAI's API endpoint, and attach the headers we just built. The body of the request contains the full JSON payload, where we define the model and the messages. We format the JSON string, injecting our user's input context into the message list. Finally, we call request function to send the request. This function immediately returns an ID. It doesn't wait for the response. The request is now in queued, and the system will handle it asynchronously. We print the request ID for debugging. Since HTTP requests are asynchronous, we need a callback to handle the response. That's what on_response does. We mark this function with callback, so the system knows it will be called automatically when the response arrives. When a response comes back, the system calls on_response, passing the request ID and the response data. Inside the callback, we first check whether the request succeeded or failed. If it succeeded, we decode the body as UTF-8 text. We parse the JSON response using cert_JSON. Then we extract the message content from the first choice in the OpenAI response. This is the generated reply from the AI. We store this content into storage under the key OpenAI_response. This way, we can retrieve it later. If the request failed, we simply print the error for debugging. Finally, we have the function get_OpenAI_response. This function reads the value we just stored in storage and returns it as a string. This allows us to access the AI's reply after the HTTP request has been completed. Now that we've deployed this Nucleus, let's go back to the Nucleus dashboard and open the HTTP module. First, we'll send a message to OpenAI. The request is sent, and after a short moment, we receive the response. Let's try sending another message. Again, the response comes back. We can also check the storage and see that the stored data has been updated with the latest response. Let's take a look at what TSS, or Threshold Signature Scheme, is. In traditional signature schemes, the private key is held by a single entity. If that key is ever leaked or stolen, the entire system is compromised. TSS improves on this by splitting the private key into multiple shares, each held by a different participant. No single party can reconstruct the full key alone, but a group of them can jointly generate a valid signature. This enhances both security and decentralization. Now let's walk through an example of a 2 of 3 threshold scheme. In the left image, we see 3 participants, Alice, Bob, and Charlie, standing around a lock. Each of them holds only a partial share of the key. No one has the full key. In the middle image, Alice tries to open the lock by herself. But with just one share, she can't unlock it. One share is not enough in a 2 of 3 scheme. In the right image, Alice and Bob work together. With 2 shares combined, they're able to open the lock successfully. This demonstrates the core idea of TSS. In a 2 of 3 scheme, any 2 parties can jointly perform a signature. But no single party can do it alone, providing both security and fault tolerance. Now, let's look at how TSS is used in the VeriSense platform. TSS plays a key role in several critical scenarios. First, in cross-chain bridge custody, TSS ensures that assets moving across chains are securely controlled by multiple parties. No single party can act alone, reducing the risk of compromise. Second, it's used in vault locking mechanisms, such as multi-signature wallets or governance systems. TSS makes sure that sensitive operations require joint authorization, which adds a strong layer of security and trust. Finally, TSS is also integrated into the monitoring consensus algorithm, helping ensure cryptographic integrity and fault tolerance in the protocol itself. In all these cases, VeriSense uses TSS to enable secure, decentralized coordination, without ever reconstructing the private key. Let's now take a look at how TSS is used in practice through the VeriSense SDK. These code examples show how to retrieve a TSS public key and generate a TSS signature using built-in APIs. On the left side of the screen, we see a function for fetching a public key using TSS. This is typically used for generating addresses, for example, in cross-chain transfers or for binding on-chain identities to TSS keys. In the code, the function getPublicKey takes 2 inputs, crypto_type, which specifies the signature algorithm, and tweak, which is used to deterministically derive a child public key from the master key share. Each unique tweak produces a different child key under the same TSS session. This allows for flexible key derivation without ever exposing the full private key. The function then calls TSS getPublicKey and returns the result as a hex-encoded public key string. Also on the left side, we have another function, sign. This is used in real transaction or authorization scenarios, where a signature needs to be generated securely through the TSS protocol. The function takes the same crypto_type and tweak as before and a message, which is the actual content to be signed, usually a hash of the transaction. Under the hood, this triggers the distributed signing process. The participants cooperatively generate a valid signature without ever reconstructing the private key. The result is returned as a hex-encoded signature. On the right side of the screen, you can see the list of supported cryptographic algorithms defined in the SDK. VeriSense supports multiple signature schemes, including P256, ED 25519, SEC256K1, SEC256K1TR, ED 448, Ristretto 255, and Exasec 256K1, which is typically used for Ethereum and BSC compatibility. All of the types without the EXA prefix, such as ED 25519, SEC256K1, and Ristretto 255, use Schnorr signatures under the hood. Schnorr signatures offer better aggregation properties, compactness, and security in multi-party contexts, making them ideal for high-performance decentralized systems like VeriSense. In summary, with just a few lines of code, developers can access powerful, secure, and flexible TSS capabilities in VeriSense, all without ever handling the full private key directly. Now, let's walk through how to use TSS in practice. First, we go to the VeriSense dashboard. Inside the TSS Nucleus, we start by retrieving its public key. This allows us to verify the identity or prepare for address generation. Next, we move to the signing section, where we can provide a message and use TSS to generate a signature. The entire process is secure and fully distributed. The private key is never reconstructed. That wraps up this session, where we explored some of the advanced features of the VeriSense platform. In the next session, we'll show you how to deploy an agent and use it within SenseSpace. Stay tuned, things are about to get even more interesting.